Now, a reaction of alkenes that branded as oxidative cleavage. Oxidative cleavage. Now, cleavage means breaking, splitting. Well, what is this? What are we doing in something called oxidative cleavage? This is a brute force. When we take an alkene like this, treat with a couple of molecules that are brutal, oxidizing agents. When you use oxidizing agents, this molecule can split into pieces. And typically it splits into this type of molecule. Whoa, look at that. This carbon-carbon bond splits right here. It forms a ketone and an aldehyde in this particular example. Okay, this is called oxidative cleavage. All right. Oxidative cleavage can happen in under two different scenarios. One is ozonolysis. That means we are using what type of molecule? O3, ozone is used. Now, for technical reason, I'm just going to write THF as in the past. It's a solvent. Don't get bothered by that. Just be aware that not water. Non-aqueous. It's something important and it's not something that you need to worry about at this point. So this need to be understood that not done in water. Step number one. The other reaction, of course, that is step number one. Step two is there are two stories. One is called reductive ozonolysis. In that case, you are using zinc, HCl, or sometimes dimethyl sulfide. Okay. So this is one type of oxidative cleavage. The second type of oxidative cleavage is permanganate oxidation. And the third one is called periodate oxidation. All right. All these three end up splitting, but not exactly like this. But the theme is still a carbon-carbon bond is split right on a pi bond. None of the other carbons are getting what you call cleaved by it. In other words, if there is a ring like this ring stays intact. This ring stays intact. There is nothing happens to the rest of the molecule. Only carbon-carbon pi bond is broken. All right. Let's focus on ozonolysis first, then deal with the permanganate. Periodate oxidation is again, it's going to follow similar suit, so we don't have to emphasize our time or put our time too much in it. So let's look at ozonolysis. Look at the structure of ozone. Ozone looks like this, and it resonates because here we have a plus charge on this one and minus charge on this one as a formal charge, and neutral 0 on this one. And its resonance structure is where 0 charge on this one, negative charge on this one, positive charge on this one. Okay. And if you look in both cases, positive charge happens to be on central atom. Ozone is not a happy molecule because oxygen doesn't want to have positive charge. This is forced to have a positive charge. So the resonance hybrid between the two looks like this. So resonance blend of this hybrid looks like this. And there is a delta minus charge on this end and delta plus charge on this end. Okay. That's something we need to understand. The negative charge is shared by these two atoms, positive charge is typically shared by this atom. The bond order is not 2, not 1, it is 1.5. Okay? People have not understood the real mechanism for this, but there is a clear indication that ozone does do some stepwise processes. It is going to form a 5-membered ring in stage number 1. I don't know how much evidence there is, but these are reported in literature and sometimes written in the book. And not everything in the book has been fully verified, but it all based on a statistical general knowledge. So you have something like this is reported to be one of the structure. Now how did we get there? We don't know. The mechanism is, people try to desperately try to show the mechanism. It's not necessary for us to know the mechanism. Just understand that these things happen. And the next cartoon that is shown in ozonolysis is this. Now how did that happen? Again, I would not be able to, and so are the authors of any book. So how did that happen? People may make mechanistic explanations for it. That requires a whole lot of learning. And what happened in this case, the cleavage actually happened. There was a two bonds between this carbon and this carbon, right? In the first step, we just got to one bond. Now there is no bond. So this is where the cleavage already happened, right? This carbon and this carbon are cleaved. Now this can undergo separation. When it's separated, people sometimes show that either that, now what happens to that oxygen? That stays a question. Or they can show that and keeping that oxygen unknown. So one of these oxygen has to somehow leave the scene, and that's why this mechanism is not clearly, I won't say understood or investigated. People know that this happens, and many times we just go along with it, right? Many times we don't really worry about. There are lots of things in organic chemistry for which mechanisms are not there. We just know this happens. That's all that matters. So ultimately, when we use zinc HCl, it's called reductive situation, because this is a reducing. Zinc essentially gives 2 electrons. It's a reduction. So that is the product. Okay. Now when we use instead hydrogen peroxide, which is considered oxidative ozonolysis, this is reductive ozonolysis. Okay. If it is oxidative ozonolysis, we have reached up to here. The step number 2, in this case I wrote ZnHCl, gives you this, right? But if it is a hydrogen peroxide, the top part is going to be still the same. Bottom part is an aldehyde which doesn't stay safe in presence of hydrogen peroxide. It gets oxidized to carboxylic acid. Okay, so that means this is the product if we use hydrogen peroxide. This is formed in, that's part of the road, but under oxidizing condition, that aldehyde gets oxidized to carboxylic acid. At this stage, you don't know, you don't really have to worry about it. Most of the time, 99% of the time, we deal with this one. 99% of the time, we deal with this one. So under rare circumstances, we might deal with this. So consider that as your final answer. What would happen if I have something like this? Ozonolysis, O3THF and zinc HCl gives you again a split. Now we normally don't write like this. It looks like we are confused. We are trying to confuse you. We write like this. By the way, this is same as this because it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Same thing. Okay. So be aware that whenever there is a cyclic molecule there, its ring is going to be opened up. This is, in organic chemistry, destroying carbon-carbon bond is not really something that people want to do. That's not really the credo. However, in some cases, we do need that as a tool. For most part, inventions are how do we build up, how do you make more carbon-carbon bonds. That is usual story. Okay, so ozonolysis has a bad name that it is destroying molecules. Here comes another example. Can you tell me what do we get? What do we get if we do ozonolyze this? It is in your best interest to start creating your own problem sets, and answer them. Well, essentially, it will split here, it'll split here, it'll split here. That much you must have understood, and it is obvious to you if you have learned the pattern recognition. This piece is same as this piece, so typically we don't write it twice. So one of the product is this, which is this one and this one. What is the second product? Another product is, see, let's look at the second piece is going to be this big. How many carbons does it have? 1, 2, 3 carbons. So it has 3 carbons and both ends are having this. Do you see that? That becomes a carbon double bond O, that becomes carbon double bond O. Okay, now this is the next piece. How many carbons are there? 1, 2, 3. Oh, it's the same thing then. So just for the sake of, I will write again, and just for the sake of, I'll write again. And you see redundancy here. This piece gave you this, this piece gave you this, and this piece, so I'm going to write 1, piece 2, piece 3, piece 4, piece 1, piece 2, piece 3, piece 4. Right? You see my point? So you are going to get 4 pieces, out of which these two are same, these two are same. So nobody in organic chemistry, we normally do not repeat them. But this is a training wheel time. When you are first learning, it's a good idea to have all pieces broken. Now, you see, if I make a slight difference, in the structure, minor difference in the structure, don't fall for it every time. This happens to be, I just happen to carefully draw this to get only 2 pieces. Okay, if I make a minute change, right, this looks the same. All I can do is stick one methyl group there and one methyl group there, right? If I did that, now you can see this piece is going to be different than this piece. Correct? This is different piece, this is different piece. Similarly, this piece is different than this piece. Why? There is a methyl substitution. In that case, I'll have to show all four. Who are the all four? I will have that, right? And that, and then that, and then that. You can see this is different than this one. Okay, if you want to master this idea, you have to make sure that you have practiced this with many examples. Okay, another reaction that can complicate your thought process is cleavage by permanganate. Now I want to bring to your attention a prior reaction, earlier reaction, where we looked at potassium permanganate, and I made a very strong case saying that cold H2O, and I said in that case H2O could be acidic or basic. Acid, usually it's an acidic condition, and I said it gives you a syn diol, gem diol, and it's a syn attack, right? This is what we have learned, and I made a very important emphasis that that's a cold condition. The reason is there is a hot condition comes along. So this is a complication in your test prepping, because permanganate may look the same permanganate, but now if you use, say, sodium hydroxide or HCl at 90 degrees Celsius, hot, if I wrote hot, now what happens is, I can keep that just for the sake of, now what happens is cleavage. What it does is it gives, just like ozonolysis, top splits like that. The bottom, however, gives you a carboxylic acid. If it is an aldehyde, if there is a hydrogen there, that becomes a carboxylic acid. If there is no hydrogen, it gives you this kind of thing. Okay, so that means if I start with that, no problem, it's going to give you that. But if I start with this, but no methyl groups on it, that means there is a hydrogen here, there is a hydrogen here. If I don't show methyl groups, the same reaction can give you carboxylic acid instead, right? And why is not really a question you should ask. You simply say, okay, I'll remember this. That's all you can do. Okay, just understood that, because in this case it is not going to give you aldehyde as in ozonolysis, it gives you carboxylic acid. Okay, this is a permanganate oxidation. You see how different these two products are. Same permanganate, water, it could be sodium hydroxide here as well, right? Under cold condition, this is aqueous. Of course, permanganate doesn't work anywhere aqueous, and as I mentioned to you, temperature cannot be more than 100 because water temperature is not going to go over 100. So this is what is the oxidative cleavage, and that should end this story.